Okay, so today I wanted to, let me make sure my volume's up here. Okay, there we go. So today I wanted to make sure that we cover a couple of basic things. One thing is basically the difference between an electromagnetic and a sound wave. We've talked about this a little bit already, between transverse waves and longitudinal waves. Sound waves are always sound waves are always longitudinal waves. They always go like this, okay? So the example we had was a slinky, right? If we use Mr. Slinky again here, what you're going to see is that if I get it tight enough so you can actually see it across the screen here, all right, so there we go. Now you're going to notice if I send a wave along here, see how I compress it up here? If I compress it and then let it go, you see that compression will come back. Now this one's also, it's not tight enough, right? So it's also trying to get a transverse wave built in there. If I go across here like I did before, I can pull it back, see that there's now here a compressed area, let it go, and you're going to see a compressed area go back and forth through here. Okay, so a longitudinal wave is one that goes in the direction, right, that the oscillation is happening. But there's something also very much more important about this. For a sound wave, sound waves can only go through stuff. They have to have stuff to go through. What a sound wave actually is material vibrating back and forth. So for that, you have to have atoms or something. Atoms, everything is made up of atoms, that's material, right? So you have to have atoms in the way that will actually allow you to move backwards and forwards. It is literally a vibration of the atoms in the air, or the molecules in the air, okay? Or you can actually hear it through the ground as well. In fact, there's a saying, put your ear to the ground, trying to get, advanced news, right? Trying to get news ahead of everybody else. If you put your ear to the ground, you could have, in the old days, and still today, if you ever see them, you can hear horse hoofbeats and other sounds through the ground much faster than you can through the air, because the denser the material, the faster the sound wave will travel through it. And if you think about it, it kind of makes sense. If you have stuff close packed by, right, when this one hits, it's going to hit this one immediately, and then it's going to hit this one, now it's going to hit the next one, and so on and so forth, and so on and so forth, right? The closer they are, there's going to be less time for that thing to have to vibrate, right? It doesn't have to move as far. It's going to be an immediate, hit and go, okay? So the denser the material is, the faster the sound wave will go. And in fact, geologists use this all the time to determine what is under your feet, okay? So if they record with the geophone, okay, it's just like this little antenna, it's just a little spring, right, that can move back and forth that has some kind of a detector on it, right? Usually an electromagnet, it has like a magnet basically on it, and it has an electromagnet underneath it, and it'll actually sense the vibration of that thing. But really, what that's doing is it's just sensing the ground wave, okay? And what they do is they can record ground shaking, right? They can record an earthquake and see what's happening. If they want to generate it because there is no earthquake happening, or they don't know what's going to happen, or they just want to see what's happening locally, what they'll actually do is get like a shotgun shell with a blank in it, okay? And they have just basically a tube, a pipe, and they feed the thing down in there, they shove it into the ground, put their geophones in an array around there in the area they want to look at, and they'll hit it. And it sets off the shotgun shell and generates this massive, if you ever hear a shotgun blast, it's a boom, okay? It travels, all waves, period, travel spherically outwards, okay? So when you let off that shotgun shell, if it's in direct contact with the ground, half of it, right, half of it is underground, and half of it's above ground. If you're really lucky and good at this, maybe most of it's underground, okay? But if you hear it, that means that you're hearing sound waves coming up from the air, through the air, okay? But if you feel it through your feet, that's because you're feeling the other part of those sound waves or the shock waves traveling through the ground. And the geophones do the same thing. So what they can then do is try and figure out the layers of rock that are under there. And they can tell the density of those rocks by how fast the wave travels through them and comes back to the geophone. If you know exactly when you hit it, because you have a sensor there, and you have another sensor way far off, you can actually determine the difference of timing, and based on the difference in timing, you can figure out the path that the ray of this thing must have taken going through the rock and coming back to that other sensor, and you can actually determine all of the layers of stuff that's under there, or if there's a void or a cave underneath you. So that's one way that they kind of survey things, is by checking out these sound waves and seeing how they move matter. And it goes faster through a denser material like rock, and much slower through a less dense material like air. There's a lot more of what you call attenuation through air. Okay, so if I'm going to draw this out, if I have a wave, and I'm going to draw this as a normal wave so you guys can see it. It's going to look like this. It's still a longitudinal wave, okay? But remember, we have our crests, and over here where we have a space, that would be our trough, okay? So this thing would be shaking. I'm just going to show the amplitude over time for you, okay? So it's going to look like this because it's amplitude over time. So if I have my amplitude on this axis, and time, or my period, I'll just put regular time over here, okay, on this axis, what I get is I'll get a crest, I'll get a trough, I'll get a crest, I'll get a trough, I'll get rarefication or spreading, right? A less dense area of waves here, a much more dense area of waves here, and you'll see that you end up with something like this over time. If you plot this out over time, you'll still get an amplitude and time graph will still look like a transverse wave, even though it's not, so be careful about that, okay? So if you have a perfect wave traveling through a perfect medium and there's no attenuation, your amplitude stays the same, the exact same, the whole way, never goes away, never changes, okay? If you don't, if you're dealing with a real-life situation, what you see instead of this, let me get a different color, in a real-life situation, things kind of shake and then they deaden and they die out, right? The waves go elsewhere, they kind of repropagate and they kind of lose energy. And the energy doesn't get lost, I shouldn't say that, it gets moved into something else, right? And what does it get moved into? Well, if you're actually moving material, what happens to your hands when you do this, right? They get hot over time. The material will also slightly heat up, so you lose some of that wave, that motion wave, into heat. It'll bleed off as heat energy, okay? So what you'll actually see in the real world, if you were to actually map amplitude over time, is something like this. Maybe your first wave is good to go, it looks a lot like this, but then you're going to see that it starts to kind of like peter off, and then at the end, you've got almost no wave at all. The thing starts to die down and lessen as you go. The amplitude of the wave shrinks and shrinks and shrinks and shrinks, okay? So one thing I want you to see here, if energy is bleeding off as you go, right? If attenuation is a loss of energy, less and less of a crest to that wave, then that means that amplitude has a lot to do with energy. And that kind of makes sense too. If you think about it in your normal transverse wave situation here, if you had like an ocean wave that looked like this, right? If you have a rubber ducky sitting up on top of it over here, let me see if I can draw a rubber ducky. Okay, maybe not, right? Here's the duck bill. Hey, look at that. Looks kind of a little bit like a duck, but not a lot. Okay, so anyway, there you go. There's your rubber ducky. If you have an ocean wave like this, think about what happens. Okay, if the ducky's up here, then it's way up at some kind of a height, isn't it? Okay, and then eventually it falls down to here, so it's going to fall that distance. So if that ducky is actually going up and down, you'll actually have a change in your potential energy of that duck. Okay, and remember, potential energy is mass times gravity times height. That duck has mass. Gravity is always gravity on Earth as far as we're concerned, right? So if you move it up and down, its height is changing, therefore you have a change in your potential energy. So waves carry energy. Remember that, okay? It's a propagation of energy, all right? No less is that true for a sound wave because it's moving things back and forth as it goes. And in fact, it moves all the way out, right? So it's also moving air like this. It's also propagating potential to kinetic energy as it goes, okay? Light wave, they're strange in a sense because light waves do this also. But sound waves move stuff. Light waves do not necessarily move stuff. Light is light. Light is actually a particle. Light is a photon. Sound is not. Okay? Sound is a movement of particles, whereas light is a thing. It is photons, right? Photons are energy. That's like one of the purest forms of energy we know of is actually a photon. So this is an interesting thing. So for electromagnetic radiation, okay, so for sound, you have to have something to move through. The denser it is, the better it carries, or the faster it goes anyway. For electromagnetic radiation, though, it will go through a vacuum. You can shine a flashlight in space. In fact, if they didn't carry through the vacuum of space, then you wouldn't be able to see sun, right? Sunlight would never ever get to you. You'd never see the sun. You wouldn't know it existed. So electromagnetic waves can carry on through vacuum. And this is strange, but I want you to remember what light is. And if you remember back to chemistry, you'll remember about atoms. So I'm going to erase all this stuff here about a rubber ducky and potential energy. You can go back and see it again if you want to, all right? So, with electromagnetic energy, if you remember, if we have our the nucleus of our atom, right? So you have all your protons, your neutrons in here hanging out, okay? And then out here, you have your electrons, right? So you have your pluses in here, you got your minuses out there. Remember that you have not one orbital, but you have multiple orbitals for any kind of atom that you're going to talk about. You have multiple places in which an electron could live around an atom. Could be here, could be there, could be way out here. And again, this is a simpler, version of it, but it works for our purposes right now, okay? So if the electron wants to jump up to an excited state, okay, what does it do? Well, it does that. It goes up this way, okay? But to get to that excited state, how does it get there? It turns out that to get to that excited state, the way that that electron moves is it actually has to take and absorb a photon. So if it absorbs a photon, it kicks it up to a higher energy state, right? And what about when it comes back down? If that electron wants to come back down to that same energy state it was at before, well, guess what it has to do? It has to shoot off a photon. Okay, so these little bits of light, these little quantized packets of light, photons, those things are constantly being shot into and out of atoms, okay, electrons around an atom, mostly the electrons around an atom, okay, and those will absorb the photon and move it up to a higher energy state, or the electron will move down, and in doing so, it'll shoot off a photon. So light definitely interacts with matter, okay? This is an important thing. Speed of light, the fastest speed of light you can get is in a vacuum, but it slows down when it comes into our atmosphere. Why? Because it's hitting atoms, and it's moving those electrons back and forth between those atoms, around those atoms, between molecules, right? If there was another atom here joined up, like for O2, it would actually have a bond between them, and you could actually have that electron go between those and actually vibrate, and you could also have some kind of similar thing like this. So molecules and atoms absorb them, okay? So when it encounters something, light actually slows down. So the denser the material it goes through, the slower light's going to go. So this is exactly opposite sound. The denser material for sound, the faster it goes, but for light, it's the exact opposite, okay? Light actually slows down as it gets to denser things, and that's what we looked at with the index of refraction before, and what we're going to see in a little bit when we actually talk about indices of refraction. This is what slows it down, okay? But look at this photon right here. It could carry on forever through the vacuum. It is a vibration. It's going through space. It's really strange. It's a particle and a vibration at the same time, but it can go on forever and ever and ever. Case in point, if you look out at the night sky, you will see stars. Some of those are actually distant galaxies. Okay, so those photons have actually been traveling through, intergalactic, interstellar space for billions of years sometimes, right? The oldest thing we've seen is about 13.5 billion years ago. So think about that. That light can travel through nothing to get to you, and it can go on forever, basically, in that state. So what the heck is it? We know what sound is. That's just vibrating atoms. But what the heck? What is that? What is this? How is it carrying on when there's nothing around it? It's really interesting and cool. Okay, so for electromagnetic radiation, what you have is I want you to look at the fact that it is electromagnetic. It has something to do with the electromagnetic force, okay? And it really helps to think about this in terms of an antenna. So if you think about an antenna, it will either, if you're pumping, voltage through it, it will give off a signal, okay? It'll give off electromagnetic radiation, okay? So if this is your antenna, right, for your radio tower here, okay? You can either put voltage into this thing, and it will actually generate an electromagnetic wave, or you could have an electromagnetic wave coming in, say if you're in your car, and the antenna on your car will actually receive that electromagnetic wave, and it will make something happen. It'll actually generate a voltage out. And then that's what your car will receive in its receiver, right? And it will turn that into sound eventually through some of the electronics. And actually, the oldest radios just directly use this to move a speaker to generate sound waves, which is kind of cool. But this thing can propagate through nothing. It can propagate through a vacuum. Okay, so what is this? What is this wave over here? Okay, So this is where things get weird, and I'm skipping ahead because we haven't gotten into the electromagnetic side of things yet, okay? But just as a preview, imagine you have a plus charge and a minus charge in here. You have a dipole antenna. You have an electrical charge. One side is positive, the other side's negative, okay? As you pump voltage into here, you have to pump it in a certain way. You have to make it a plus, and then a minus, and a plus, and a minus, and you have to basically change your voltage, has to go up and down as you go to get anything to happen with your antenna. You have to have alternating current, okay? You have to pump in a positive voltage and then like switch it so it's the negative voltage you're pumping in, so you actually get an alternating current. When you do that, what you're doing with these charges, these plus and these minus charges, is actually moving them up and down along this antenna, along the length of the antenna. And when you do that, these things affect, because they are a positive or a negative charge, they actually affect the electromagnetic field, right? So what they do is they actually drag the electromagnetic field around it, okay? So as this thing goes up, it's dragging up, it's causing an effect as this propagates upwards, up to here, you know, to here, to here, to here. That positive charge is actually taking that electromagnetic field and it's dragging it along with it, okay? And so what you get is you get an electromagnetic field that's following along with this, and then when the negative voltage comes along, it's attracted back down here, so then the thing comes back down, and you get that coming back down this way. So you actually get a propagation of the electromagnetic field. You're actually taking and making a ripple to the electromagnetic field that exists everywhere in space. This is really strange, okay? So there are these things called fields that are around you. Gravity is one. You're used to that. In fact, we kind of talked about that last year a little bit with time dilation, stuff like that. You can actually take this field that just exists in space, right? It exists everywhere. And if you put a mass on it, all of a sudden you warp that field. Well, instead of mass, this is another field, and it uses charge or electricity or magnetism, because they're the same force, they're flip sides of the same force, right? And it exists everywhere. But when you move a charge through it, if you move a charge up, it will flex with how that charge moves. And so you're actually creating a ripple in the electromagnetic field. And this exists everywhere in the background. And that's why electromagnetic waves can propagate through anything, okay? Which is really strange, isn't it? It's kind of a mind-blowing moment, right? That something as simple as your car antenna, right, or receiving something over your TV antenna, is actually a ripple in the electromagnetic field that exists everywhere, which is pretty cool, okay? So, when you get an electromagnetic field, which we're going to talk about a lot later on, if you put a charge in it, it warps the field. And if you move the charge, that field will warp up and down around that charge because the charge affects the field, just like a mass affected the gravitational field, okay? So, if you put Earth here, all of a sudden anything that's next to it, say like the moon, will start to try and fall around it. If the Earth moves, then the moon maybe misses it and then tries to go around it, right? Because it's being affected by the gravitational field. Well, this is the same thing. Anything that will interact with the electromagnetic field will be affected by an electromagnetic field that is going up and down, right? And conversely, if it can affect the electromagnetic field, it can change and create ripples in that field. All right? Now, there's another thing I want you guys to see, because electromagnetic energy is all about light. Light is electromagnetic energy, because it's the thing that makes the electrons bump up and down, back and forth, through an atom, because they get absorbed, a photon gets absorbed into an electron and makes it bump up, or it gets emitted by an electron and boom, the electron falls back down towards the nucleus, right? And light goes off, okay? So photons are really the thing that make electrons move around. So that is actually the carrier of the electromagnetic force. Electrons would never move if it weren't for photons. And another thing we're going to get into later, okay? This is the electrical field I just talked about. But it's an electromagnetic force. They're related. They're at 90 degrees to each other. They're perpendicular. So whenever the electrical field goes up like this, you get a similar thing. And I'm probably going to draw this wrong because I'm a little bit out of the habit here. But whenever this goes up, if this is the E field, okay? This is your E field, your electrical field. You also have a magnetic field that is also affected by your electrical field. Whatever happens in your electrical field affects your magnetic field. Whatever happens in your magnetic field also affects your electrical field. So if this is happening here, let me draw some arrows, right? You have other things along the way. Anything that's in here that would be affected would be carried up by, you know, or down by the electromagnetic field going up and down. And you know I can do a better job of this. Let me put a midline in here. Let's call that the midline. All right. So as things go up to the E field, well, it's kind of weird because things are going to be coming out at 90 degrees for the B field. Okay, so this right here is the electromagnetic field. Okay, and this I'm going to try and draw at an angle, but this, whenever this goes up, it's going to affect the magnetic field. All right, and this is going to affect the magnetic field whenever it goes down. And same deal here. This is a really terrible, I should be drawing this at a more of an angle so you guys can see it better. That's pretty poorly done, but these are all at 90 degrees. Ugh, 90 degrees to one another. I'm just trying to show this into, so the B field, magnetic field, will be going into and out of the board, whereas the electrical field will be going up and down. They're always at 90 degrees to each other. And we're going to talk about a right-hand rule later on, 2 of them actually, that have to do with everything with how electricity and magnetism are related. But remember this, light waves will always have 2 parts to them. They'll actually have an electrical component, and they'll have a magnetic component. And whatever one is doing, the other is doing 90 degrees out of phase to the other. Of the 2 that can be polarized too, we talked about polarizing filters. Remember this guy, right? If we have this, we're actually cutting out light, half of the light, because it's affecting basically how the electrical field, you know, goes through here, right? Is propagated through. These guys, these transverse waves, can be polarized. Light can be polarized. Sound never can. Okay? Sound will always be just back and forth. That's the only thing it can do. Transverse waves, on the other hand, can absolutely be polarized, and they can be filtered out too. All right, so that's kind of what I have to talk about. If we want to talk about energy levels with electromagnetic fields too, let's go ahead and do that. And I've been talking so long. Sorry about this, guys. I've been talking so long that the thing timed out on me. But one thing I want you to see is perfect time of day for this, hopefully. If I get this right in line. Maybe. Come on now. This isn't that hard. Okay. If I look down, oh, maybe make you sick here. You'll notice that with this, white light is never just white light, right? It's always a prism, okay? It's always a made up of a bunch of different wavelengths of light. If I can get that closer while still holding this. But you can actually see that there is multiple colors to that. So every bit of white light is actually made up of a number of different wavelengths of light, and each one of those things is independent. Each one of those things has to do with energy. The closer to blue, past blue it is, the shorter the wavelength, the more energy it has. And again, if we wanted to create that, again, the faster we pump the voltage up and down, the faster we oscillate that, right? The faster we oscillate that thing, the more we shrink the wavelength, because it'll go back and forth really, really fast, right? Hit that high point, crest to trough to crest to trough to crest, right? If we do that really fast, the faster it goes, the shorter the wavelength will be, the higher the frequency would be, the more energy is dumped into it. So if you get to a higher voltage, a higher frequency of voltage, you can start to create, instead of electromagnetic waves that you can't even see because they're too long, right? You can maybe start to create things like microwaves that you still can't see, but can warm up your body. You go a little bit faster, all of a sudden you can start to create things that you can see, like visible light. You keep going faster with it, and you'll eventually be able to get to things like X-rays that have so much energy they can just pass straight through your body, okay? And as they go through, they have more chance to penetrate through, more energy to carry on through, and eventually you get to things like gamma rays, this whole wide bandwidth of things that I'll show you guys a chart on, okay? That's basically all I have for electromagnetic versus sound waves, but important differences between the two, and I want you guys to be able to see that, okay? And don't forget, anytime you see light, almost invariably is going to be made up of multiple wavelengths of light. Now, there are exceptions to this, and one of the major ones is an LED, okay? And I'll talk to you guys about that one later when we get into electricity. It'll make a lot more sense then. But basically, they control how far an electron can jump. And by doing that, they only let one wavelength of light out generally.